So in this video, we're going to talk about the key characteristics of the functions that we're going to be studying in Algebra 2. So Algebra 2 is all about the study of functions, and we're going to be learning about all sorts of functions this year. When you talk about functions, we like to group them into what are called families. And so families of functions have similar characteristics, and it just really helps us keep us more organized with the information that we're learning. So you've already seen the quadratic family of functions back in Algebra 1. So every family of functions has a parent function, which basically represents the most basic member of that family. So for the quadratic family, that basic parent function is f of x equals x squared, which you can see in this graph. And so here I've shown you 4 different members of the quadratic family. Obviously, these don't represent every member of the quadratic family. I've just given you 4 examples. And notice that these all represent variations of this quadratic parent function. So when I think about parent functions and families of functions, I like to think of this analogy, okay? So the parent function is kind of like if you have vanilla ice cream, right? So vanilla ice cream is our most basic ice cream. It's the original flavor. And then if I add chocolate chips to it, I get chocolate chip ice cream, right? So chocolate chip ice cream is still a member of the ice cream family. It's just a variation of the parent ice cream. I can add 2 flavors if I want, right? I can add mint to it and I can get mint chocolate chip ice cream, which is still a member of the, family of ice cream. It's just 2 variations on the parent. Similarly, if I had chosen to add strawberry instead of chocolate chips, I could have gotten strawberry ice cream, which is also a family member. And if I make 2 variations and I add strawberry and banana, I get strawberry banana ice cream. Okay, so all 4 of these are still members of the same family. They just represent different variations of the parent, which is vanilla ice cream. So how do we group functions into families? Okay, so you may be wondering, how do we decide which members go into which family and things like that? Well, what we do is we look for common characteristics. Okay, so if we look within a family of functions, a lot of those functions will have very similar characteristics. And so the characteristics we're going to look at are going to be domain and range, intercepts, asymptotes, symmetries, and maxima or minima. And these are going to allow us to group the functions into categories. So remember domain and range. So remember the domain is all possible x values of a function, and the range is all the possible y values of a function. We can also talk about the intercepts of a function. Remember the x-intercept will be anywhere the graph crosses the x-axis. So you can see in this example, it has 2 x-intercepts, and notice that at the x-intercept, the y value will be 0, right? So we have an x-intercept at -2, 0, and 1, 0. The y-intercept will be where the graph crosses the y-axis. So at this point, the x-coordinate is going to be 0, okay? So notice this graph has a y-intercept at 0, -6. Some graphs will also have asymptotes. Okay, an asymptote is a line that we draw onto the function, okay? It won't be like if you graph it in Desmos, it won't include the asymptote. The asymptote is something that we have to add in. But we know it's there because a vertical asymptote, for example, will be a line that the graph does not cross, okay? So this is a rational function. Notice that if I draw in the line x equals 0, this graph is going to get really, really close to x equals 0, but it's not actually going to cross it. Okay, so this graph actually has 2 pieces, but notice that it's not ever going to cross x equals 0. And so what a vertical asymptote does is it tells us what is the x value where the y values are going to head off into infinity. Okay, because you can see here the y values are heading off into positive infinity, and then here the y values are heading off into negative infinity. And that's happening around x equals 0. Some graphs will have a horizontal asymptote, and you've seen horizontal asymptote back when you talked about exponential functions. So graphs can cross a horizontal asymptote, okay, and some graphs do that. Exponential functions don't cross the horizontal asymptote. And remember, a horizontal line will have an equation y equals some number, right? And what this is it's going to be a value that the function approaches as the x values go to infinity. Okay, so notice that here, this x is heading to negative infinity, but then the y values are getting close to y equals -3. Okay, so that's a horizontal asymptote. So some graphs will also have what's called rotational symmetry, okay? And remember back from geometry, rotational symmetry happens when you use a point as like a pivot, and then you rotate your figure a certain number of degrees, but then your figure stays unchanged, right? So this star if I rotate it 72 degrees about this central point, it's still going to look the same. And so we would say that this figure has rotational symmetry. And that can also happen with graphs. This is the graph of a cubic function. And what happens is if I use the point 0, 0 as my pivot and I rotate this graph, it'll still look the same, right? You can see this piece up here will come down here, and then this piece down here will come up here. So this graph has rotational symmetry about the point 0, 0. Some graphs will have reflectional symmetry, right? And this is something that you saw back when you studied parabolas. And reflectional symmetry happens when there's a line. That line is usually called the axis of symmetry. And if you can reflect the graph across that line and both pieces will match up, it has reflectional symmetry, right? And back in geometry, you talked about that, like when you took a figure or a shape and you folded it in half, and if both sides matched up, then it has reflectional symmetry. So some graphs will also have a minimum value, and you saw this once again when you were studying parabolas. Remember, if it's an upward facing parabola, then it's going to have the vertex is going to be a minimum. And what happens at the minimum is that the y-coordinate will be smaller than all the other points on the function, right? So this quadratic function has a minimum of -4 at x equals -3. Just like with quadratics, you did see a maximum. This is an example of a maximum with actually an absolute value function. And that will occur at a point that has a y-coordinate that's larger than all the other points on the function. So you can see this y-coordinate at -2 is going to be a maximum because all the other y values of this function are below that. So this absolute value function has a maximum of -2 at x equals -3. So when we're studying functions and working and grouping them into families, we want to study these key characteristics, right? So the domain and range, intercepts, asymptotes, symmetries, and maxima and minima. And that's something we're going to be seeing a lot more of as we work through studying these functions. So just a quick preview of coming attractions. So I kind of give you a little bit introduction into families of functions and parent functions. And we're going to learn about transformations, which you did start to see in Algebra 1. So remember those reflections, vertical stretch or compressions, shifts up or down, left or right. And you can actually turn the parent function like f of x equals x squared into another member of its family. Okay, so we're going to get to that in a few lessons, but I just wanted to kind of give you a heads up of what's going to be coming up soon.